The following, read that quietly and find an answer. You don't have that? Okay, read it up here. Why would it be slow?
Low activation.
Okay, strong bonds in the reactants. I think that's our best answer here. Another option would be a very unstable activated complex or strong bonds in the reactants. All right, reaction mechanism. Here we go, guys. Eventually, this is easy. Eventually, it clicks. Eventually, students can actually write their own reaction mechanisms. Starting to teach it and tie it into rate law is confusing. So everyone sit up, breathe in. No daydreaming. Focus, focus, focus. Here we go. What time is it and how much time do I have? Because I hate it when people walk out confused. We have plenty of time today. I love Mondays. Mondays are long. I'm thinking some of you will be confused. Most of you, it might start to click. So first of all, similar to Hess's law, the balanced chemical equation provides information about the beginning and the end of a reaction. So every time I give you a balanced reaction, that's actually the net of the beginning and of the end, but it doesn't really show you what's going on throughout the middle of the reaction. The reaction mechanism gives you the path to the final reaction. It's the details that in high school chemistry we ignore. In college level chemistry, when you get to this chapter, you start to focus on the details. So, by the way, reaction mechanisms are theoretical. I've had students working in Cosmos and labs where they work on research, trying to figure out a reaction mechanism. It can take years and years to work up a reaction mechanism, and then finally, when they work it out, they publish it. Even though it's theoretical, that doesn't mean they don't exist. Most published reaction mechanisms are very close to the reality of what's going on. Reaction mechanism provides a very detailed picture of which bonds are broken and formed during the course of the entire reaction. So every step is called an elementary step. All of your elementary steps, you might have 1, 2, 3, 4 elementary steps, they must add up to be the net reaction at the end. All right, let's go back to this. Dr. Doofenshmirtz. He's given this chemical reaction. He sets up a list of experiments and he determines that this reaction is zero order in carbon monoxide. So when he doubles and triples and quadruples carbon monoxide, nothing goes. It has to be there, but it does not have any impact on the speed. Today, by the bell, you will graph why it's zero order. Dr. Doofenshmirtz, through his series of experiments, discovers that when you double NO2, the rate quadruples. If you triple this, the rate goes up 9-fold. It's second order in NO2. Well, you have the net reaction, and we have to come up with a reaction mechanism that justifies this being second order. Let me say that again. Your reaction mechanism that you're going to propose, that you will start writing, must give you the net reaction, has to be consistent with the net reaction, and it must be consistent with the rate law. Okay? Second order is what type of reaction? Collision reaction. So for a second order reaction, NO2 must collide twice in your proposed mechanism. So watch. Here's the first proposal. NO2 collides with NO2 to form. Now, in your proposed hypothetical theoretical mechanism, this is step number 1. We're going to have NO2 collide with NO2, and now this must be a balanced reaction. I need 2 nitrogens and I need 4 oxygens. Let's propose it like this. You have 3 oxygens here and 1 oxygen here. Now I like that because NO is one of my products. This is now called an intermediate because I'm going to get rid of it. Okay, now I know I need to get rid of the NO3. I propose that, but it's not part of the net reaction. So after I propose that, I have to get rid of it. Well, I also have to look at my balanced reaction. I need carbon monoxide as a reactant. Carbon monoxide collides with my intermediate. Is this a balanced reaction? 1 nitrogen, 4 oxygens, 1 carbon, that's the balanced reaction. I also love this hypothesis because it gives me the net reaction. But wait, there's more. I'm not done. Now, this is step number 2. Now, the other cool thing about this is my reaction mechanism, step 1 and step 2, they give me the net reaction because the NO3 cancels. It has to explain the law. What was the rate law? Second order in who? NO2. And here it is. This is where people daydream. They don't hear what I'm saying, and it takes days for it to click. The reaction mechanism, the rate law is equal to, this is the most important sentence of the semester. The rate law is equal to the term rate equals K times all of the reactants colliding prior to the rate determining step. The rate determining step is, no. The rate determining step is the slow step. So this is going to be the slow step. This is going to be the fast step, and we are about to graph that so it clicks. Now, if you remember from last year and at the beginning of this chapter, when I taught collision theory a couple days ago, what makes a reaction slow is the height of the energy barrier. Who lives up here? What's that called? Activated complex. So what makes a reaction go slow is how unstable that thing is up there. So these two are going to collide prior to the energy barrier. This one's going to collide after the energy barrier, and all of that will click in time for the bell to ring. That's my goal. It might not. So first of all, what is an intermediate? The species which appears in an elementary step, but it's not a reactant and it's not a product. An intermediate is something that you propose that is only there for a few minutes. Okay, now, once we start to graph this, things should start to click. Here we go. We're going to label the first one slow and the second one fast. Time-wise, this reaction takes a long time. Once this, because the complex, the activated complex is unstable, once this reaction goes, this one goes really fast. So the rate determining step is the slowest of the elementary steps, again, because the activated complex is so crazy unstable. By the way, what is the activated complex here? Can we draw it out? In your notes, do this. It's NO2 colliding with NO2. Put a circle around it. That's the activated complex. And that thing, these guys are colliding. The electron clouds are mushing together. It's crazy unstable. So it slows that reaction down. When these two things collide, it's not unstable. So that one goes really fast. We don't have to worry about the second step. All right, now we're going to graph it. Graph it. Did I give you an XY axis? Yeah. Yes, good, cool. I'm going to teach you how to graph these. On the test, you will eventually propose your own reaction mechanism and you will graph it. Step number 1, NO2 collides with NO2. Now, just for fun, can we put that activated complex right here? NO2 smooshes into NO2. That's your activated complex. The activated complex is theoretical. You cannot isolate it. It's dynamic. It exists for a split second, fraction of a second. So you can logically deduce it, but you can't prove it. You can prove it through logic, but no other method. Now, in this valley, you guys have never seen an energy barrier with a valley like that. So in that valley is your intermediate. Who is the intermediate? Look up above or on the other page. It's NO3. NO3, this is step number 2. Draw an arrow from carbon monoxide to your intermediate. That's your second collision. This is the slow step. This is the fast step. Okay, so again, all we're doing is we are actually graphing the reaction mechanism. Collision number 1, forming a very, very unstable activated complex. Label this, guys. This is the activation energy. This is not the activation energy. This is the activation energy. It's called the rate determining step. Now, look at the rate law. Let me write it up here. Rate equals K. This is where it should all click. This is it, right here. Dr. Doofenshmirtz. He is going to go double NO2. If he doubles NO2, he's doubling not just NO2, but he's also doubling NO2. If he doubles NO2, he doubles NO2 and NO2, so the rate goes up by what? 4. Now, what if Dr. Doofenshmirtz, guys, what if Dr. Doofenshmirtz doubles carbon monoxide? No impact, because that's fast. It's 0 order in carbon monoxide. Okay? What if it looked like this? Now, double NO2. Double. If you double NO2, the rate goes up by what? 8 order. 2 times 2 is 4 times 2 is 8. The rate goes up 8-fold. It would be what order in NO2? 8th order. If Dr. Doofenshmirtz had doubled NO2 and the rate went up 8-fold, then he would come up with a mechanism where 3 of these are colliding. That would be 3rd order. Okay? Now, watch again. Guys, watch again. If I double carbon monoxide, what happens? No impact, because that's already fast. What if I increase this times 10? What happens to speed? Nothing, because it's 0 order, because it's already fast. Now, I'm going to regraph this. What if, and once I get it wet, it's still wet. Okay, so what if I graph it like this? Give me the rate law if that was the key fact. NO2 squared times carbon monoxide. It would be 1st order in carbon monoxide. Now, if I double NO2, it's going to go up. That would account for a quadrupling. And now if I double this, it would count for another doubling. So if it was 2nd order and 1st order, doubling this and this would give you an 8-fold increase. The rate law is based on the activation energy, the rate determining step. Now, if this was the graph, if that was the reality of this reaction, then Dr. Doofenshmirtz would label this fast, slow, and if it was fast, slow, then this would be the rate law. Raise your hand if this is starting to click. I just need it to start to click. Raise your hand if none of that makes any sense. Okay. I'm happy. That's good enough. Quiz tomorrow? No. No. Okay. Okay, now the analogy. Hey guys, watch. Let me give you the analogy. Okay, the Rockies. Y'all know the Rockies. We live west of the Rockies and the East Coast is east of the Rockies. Watch this. The rate law is rate equals K times all of the collisions west of the Rockies. The rate law is equal to rate equals K times all of the collisions west of the Rockies. This one doesn't count. That's on the east side. Only the collisions west of the Rockies is part of the rate law. Okay? If you want carbon monoxide to be part of the rate law, then this has to be the energy barrier. You put the Rockies over here, and then it's west of the Rockies. Right now, it's east of the Rockies. It's 0 order. Anything colliding east of the Rockies on the east coast is 0 order. Only things west of the Rockies is part of the rate law. Izzy?
So because that second, I guess, increase isn't higher than where CO is, it's not part of the rate law?
Because this is a reaction, this is a collision, but that happens really fast because that activated complex is stable. So if you double it, if you double the concentration, that will double. It will. If you triple that, that will triple. But is that part of are you gonna measure that? No, because what determines the rate of the overall is this one. So I'm not saying that doubling, tripling, quadrupling doesn't increase that speed. It does, but it's not measurable because this is the slow step. Yes, questions? Alex? Yeah. Zach?
So let's say we were given the rate law for this and it was third order where like CO was first order. How do we know that it's like a higher peak in the second place and not that CO is just a part of the first reaction?
Because you have to listen to two sentences that Hampton says, and these are the most important two sentences for this chapter. First of all, the rate law is composed. These are the two sentences, you have to listen to them and they have to click. You have to understand what they're saying. The rate law is rate equals K times all of the collisions prior to the rate determining step, second order, first order. My analogy is the rate law is rate equals K times all of the collisions west of the Rockies. This is prior to the energy barrier, prior to the rate law. This is the rate determining step. That's the rate determining step right here. It's the slow step. So if it was second order and first order, this would be the rate determining step.
So it can't be that it's CO plus NO2 plus NO2 at the beginning? Like before even?
Are you saying, you're thinking these guys collide?
Yeah.
Okay. When I showed all three NO2s colliding, that's not how it works. That's called a ternary collision. We're going to talk about that numerous times. I don't want you proposing ternary collisions because when two things collide, what two things must be true for the reaction to go? They have to have enough kinetic energy and what? They have to bump their asses in the right direction. What are the chances? Think about it. What are the chances that three things collide in the proper orientation? It's just not going to happen. Not going to happen. Okay, so that's called a ternary collision. I don't know. I've never docked points on the test or homework when you do that, but I bark at you because it's inappropriate. It means that you're not a good chemist. You don't really understand kinetics. I'm like, I'll give you a sad face, grumpy face. Like, what are you doing? What are you doing? Okay, here we go. And if it's not clicking yet, it will click. This actually becomes easier. Okay, go give me all of the intermediates. Cross out your intermediates and look for a catalyst. Cross out all of the intermediates and look for a catalyst. Cross out Huber. Do you see any other? Hypobromous acid. Cross out Huber and hypobromous acid. Those are intermediates.
So how do you know that
It exists for a moment and then it's consumed. It's produced and consumed. Anything that's produced and consumed is there for a while, but then it disappears. Hypobromous acid, same thing. Now, the rate law is first order in HBr and first order in oxygen. Label these fast, slow, slow, fast, slow. Label them faster, slow. Label all three steps. There is one rate determining step. These two must collide prior to the rate determining step west of the Rockies. Okay, and what's the answer? Slow, fast, fast. They are slow, fast, fast. Okay, now let me switch it up so that it's bad. It's slow, fast, fast, and that's consistent with the rate law. What if I did it wrong? What if I called it fast, slow, fast? Now what would the rate law be? Second order in HBr, first order in oxygen, that would be wrong. Let's make another mistake. Let's call the last one slow. Now what would it be? Yeah, right. Fourth order in HBr, 1, 2, 3, 4. First order in oxygen, fifth order reaction. That is also not what he determined. Okay, the last one can't be the rate determining step. The middle can't be it. The first one must be the rate determining step. It's the only one that's consistent with the rate law. Okay, Tanya.
So when you determine the rate law, you count, like for example, for HBR, you just count from the slow one and upwards. So for example, if it was in the middle, you would count from that one up.
Yes, so guys, here, these two collide prior to the energy barrier. If I had labeled it slow here, then it would be, these two are prior to the energy barrier, and so it'd be second order, prior to the bump. Okay, are we gonna graph this? I think we have to graph it. We're unable, hey guys, yoo-hoo. We are unable to determine, to detect the intermediates. Does that disprove the proposed mechanism? No. Steps 2 and 3 are fast. Intermediates can exist for minutes. If you're lucky, maybe as long as a half hour, but they don't exist for very long. Activated complex at the height of the barrier, there's no way you can isolate those. Intermediates you can isolate. Do you guys remember the story I told you not too long ago where I dumped carbon tet down my arm? So, my lymph nodes got infected because of that. It took a month to clear it out of my system. We were trying to isolate an intermediate, it was Monsanto Roundup. Monsanto Roundup, and there was an intermediate inside the plant. So it was already on the market. You could go to Home Depot and buy it to kill your weeds. They didn't really understand what was really going on in the biochemistry. They just knew that it worked. There was an intermediate. We could see it on the TLC. You turn off the lights, use the black light. You could see it. We would scratch it out, isolate it, shoot it through the mass spectrometer. But by the time we got to the mass spec, it had decomposed. It was gone. So the problem, the reason I contaminated myself, I was going so fast. It was like the end of summer. And we were running, I'm seriously, we were running down the hallway from the greenhouse to the lab trying to isolate it, and every time we failed. We could see it, we knew it was there, but we couldn't identify it because we couldn't run fast enough. There you go, there you go. In fact, our researcher got so frustrated with us, one time, this was Dr. Arp, one time, because the grunts, grad students, and the SRAs, the staff research associates, they would do all the work. The doctor, he would just publish, that's all he'd do, publish and get the money and write the grants. One time, he actually came to the lab, went to the greenhouse, said, I'll show you how to do it. And it was so funny watching this old guy run down the hallway, and he still failed. It's like, dude, you didn't run fast enough. Fail, that was a fail. So, we could see the intermediate, we just couldn't prove what it was, we couldn't identify it. That doesn't mean we didn't identify it right. Okay, here's an uncatalyzed pathway. Can you guys cross out the intermediates? Oh, is there a graph? Oh, graph it. Why don't I have a graph? That's Hoover? Graph it. I'm walking around. I don't know what happened to my graph. You can't graph it. I'll fix my PowerPoint. I lost it. That's sad. John, have you already picked up your poster? Pick it up here after school.